Now that we can take partial derivatives, we're going to look at taking partial derivatives for functions of more than two variables, and we're also going to look at taking higher order partial derivatives. While we can't really visualize functions of more than two variables easily, we can consider that for a function of three variables or even more, a partial derivative is still going to measure change in one variable while we're holding all of the others constant. So geometrically, we're still taking one-dimensional slices through n-dimensional space and computing ordinary derivatives. We can also take higher order partial derivatives, which are going to measure the rate at which our rates of change are changing. We'll still use similar notation. We have both subscript notation and operator form, where in the operator form and in the subscript notation, the letter down towards the bottom indicates the variable that we're differentiating with respect to, and our rule of thumb is that we're going to treat every other variable as a constant. While our formulas may look more complicated, our computing strategy remains the same. We'll choose the variable we're differentiating with respect to, treat everything else as constant, differentiate using our single variable rules, our product rule, our quotient rule, our chain rule, etc., and then we'll simplify, and if we're asked to find the derivative at a point, we'll plug it in. Let's take a look at an example. Here we're going to look at the function f of x, y, z, and we're going to find the partial derivative with respect to x, the partial with respect to y, and the partial with respect to z. So our partial with respect to x, we're holding y and z as constants. So in the term x squared y, since y is a constant, we're going to get 2yx, or of course we could write that as 2xy if we want. The term yz cubed doesn't contain any x's. That means its derivative is 0 when we're differentiating with respect to x. Our last term is e to the xz, so we know since that's exponential, it's going to repeat, and then we're going to multiply by the derivative of the exponent, and that is going to be z when we differentiate with respect to x. So we get 2yx minus z e to the xz. Now we'll differentiate with respect to y. So in this case, in the first term, the x squared is a constant. The derivative of x squared y is x squared. In the middle term, the z cubed is a constant, and so our derivative of yz cubed is z cubed. The last term contains no y's. That means the entire thing is treated as constant and its derivative is 0. When we differentiate with respect to z, there are no z's in the first term, so the derivative of that is 0. In the second term, differentiating with respect to z gives us 3y because y is a constant, and then we get z squared. In the last term, because it's exponential, it will repeat, and we'll get the derivative of the exponent, multiplying that, which is going to be x. So if we want, we can rewrite that as 3yz squared minus x e to the xz. Because partial derivatives are themselves functions of the variables in question, that means they have derivatives. We can take those derivatives called higher order partial derivatives. So here we have f sub xx is the second partial derivative with respect to x. F sub yy is the second derivative of f with respect to y. And f sub zz is the second derivative of f with respect to z. When we do these derivatives, we're differentiating our first partial again with respect to the same variable. So we're looking not at the rate of change of the curve in a particular direction, but now we're examining its curvature in that coordinate direction. We can also mix it up a little with our mixed or cross partial derivatives. If we denote f sub xy, that means that we are taking the partial derivative of f with respect to x first, and then differentiating that with respect to y. If we take f sub yx, that means that we are taking the derivative of f with respect to y first, and then differentiating that with respect to x. And we can define several partial derivatives, mixed partial derivatives, similarly. Notice that the order matters in the notation. The letter that comes first tells us what we're going to differentiate with respect to first. The letter that comes second tells us what to differentiate with second. And we'll see in a moment a nice theorem that tells us that in particular cases, the mixed partials f sub xy and f sub yx are equal to one another. The theorem I just mentioned is called Clairaut's theorem, and it tells us that if our second partial derivatives are continuous near a point, then f sub xy and f sub yx are equal at that point. Most of the functions we'll look at are considered smooth, which means they're going to be continuous on the points in their domain. So we can use this assumption pretty commonly. And we'll get to use it a lot when we look at Taylor expansions and optimizations. All right, let's take a look at some higher order partial derivatives. So here we want f sub xx. So the first thing we're going to have to find is f sub x. So we'll differentiate with respect to x. That's going to give us 3x squared plus y squared plus the derivative of sine x is going to be cosine x, so we'll get z cosine x. F sub xx says differentiate that again with respect to x. So our first term gives us 6x. Our second term gives us 0 because the derivative of y squared, treating that as a constant, is 0 when we differentiate with respect to x. And our last term is going to give us negative z times the sine of x. Now we'll do f sub zz. So first we find the first partial derivative with respect to z. Well, the first two terms don't have z in them, so their derivatives are 0. And the last term, sine x, is going to be a constant when we differentiate with respect to x. So we just get sine x, which means that when we differentiate twice with respect to z, since there's no more z's in this function, the only thing that's left is this constant sine x, constant with respect to z, which means the second derivative with respect to z is 0. All right, our next example says we're going to find the 4 second partial derivatives of the function e to the x squared y. Now, this isn't a function, there's no z's in here, so there are only 4. There's no derivatives with respect to z because the entire thing is a constant. So the 4 we're looking for are going to be f sub xx, f sub yy, f sub xy, and f sub yx. Those are the 4 we're looking for. And so let's start with f sub xx. Let's look at f sub x. We know it's exponential, so it repeats itself, and then we multiply by the derivative of the exponent. Well, the derivative of the exponent with respect to x is going to be 2xy. We can then find f sub xx by taking the derivative of that. So now we have to use the product rule. So we take the derivative of the first expression, which is e to the x squared y, times the derivative of x squared y, multiply that by the second expression, 2xy, and then we're going to add to that the first expression unchanged times the derivative of the second, which is 2y. So we get e to the x squared y times 2xy all squared plus e to the x squared y times 2y. And if we wanted to, we could simplify further, but I'm going to stop there. I'm now going to return to this function, and I'm going to look at what is f sub xy. So again, we have to use the product rule. I'm going to take the derivative of the first expression with respect to y this time. So it repeats itself, and then the derivative of the exponent is x squared. And I multiply that by the second term. And then I'm going to repeat the first term, e to the x squared y, and multiply by the derivative of the second term with respect to y, which is then 2x. And we can tidy that up a little bit if we want. We'll get e to the x squared y times 2x cubed y plus e to the x squared y times 2x. And if you wanted to factor out an e to the x squared y, you could. I'm going to stop there. So we've got 2 of our 4 done. We have f sub xx and f sub xy are done. Now we're going to go on to the y derivative. So f sub y is going to be e to the x squared y times the derivative of x squared y with respect to x, which is x squared. Take the derivative of that again with respect to y. We're using the product rule. So I'm going to take the derivative of the first piece, e to the x squared y, times the derivative of y, which is x squared, times the second piece, plus the first part of the function, times the derivative of the second with respect to y, which is 0. So that actually drops out. So I thought about that incorrectly. That's not really a product when we're thinking about it in terms of y, because the second term is just a constant. So here we get x to the 4th e to the x squared y. Now we'll do f sub y sub x. So now I'm going to take the derivative of f sub y with respect to x. When I do that, again using the product rule, I get e to the x squared y, the first part of the function, or the derivative of the first part of the function. So that's e to the x squared y times the derivative of the exponent with respect to x. So I'm going to get 2xy times the second function, plus the first function repeats, and I multiply by the derivative of the second, which is 2x. And notice Clairaut's theorem applies here. If we look back at our f of xy right here, and my f of yx, they are in fact the same. All right, we'll finish up with an example of some more mixed partials. So we'll start with f sub xy. So clearly we need to do f sub x first, the partial with respect to x. So that means the y and e to the z term in the first part of our function are going to be constants, and so the derivative with respect to x is just y e to the z. The second term contains no x, so its derivative is 0 with respect to x. From there, we can compute f sub xy. It's pretty straightforward, right? E to the z is just a constant term, so we get e to the z. We can also do f sub xz, and we're differentiating now with z being constant, and so that's going to be y times e to the z, because the derivative of e to the z is itself, and the y acts as a constant, so we just multiply it in front. The last one we're asked to do is f sub yz. Obviously, there's a few more we could do, but we're not doing them all. So f sub yz, first I have to do f sub y, and that is going to be x e to the z, because those are constant multiples of y when we differentiate with respect to y, plus 2zy. Now I'm going to take the derivative of that with respect to z. So in the first term, it's exponential with respect to z, so we're going to get x e to the z. And then the second term, the 2y acts as a constant multiple of z, so we get plus 2y. So what we've seen here is that we can take first partial derivatives for functions of many, many variables. We're just going to hold all of the variables constant except for the one we're differentiating with respect to. We can also take higher order derivatives because a partial derivative is itself a function, which means it has a derivative. So we can differentiate again, both with respect to the term we started with, and we can also mix them up and differentiate in 2 or more variables. And Clairaut's theorem tells us that if we have a function that is continuous in over some area, then the mixed partials are going to be equal to each other regardless of the order in which we take their derivatives. Up next, we'll be looking at the chain rule for partial derivatives, which will allow us to compute partial derivatives for functions that have been parameterized.